Hi there, welcome to my presentation on the World Congress of Universal Logic. I hope you enjoy it. I'm going to present another talk on Christine Ladd-Franklin's logic. I feel very glad that there is a revival of interest on her logic. And incredibly as it may be, there isn't much overlap between my talk and the previous talk, because the previous talk was about model logic, and the perspective I will adopt here is about Aristotelian syllogism and Boolean algebra. So there is a little bit of overlap, but only on the basics. And then when we move to more advanced stuff, it's completely different path from the previous presentation. So, okay. There are many reasons for the community of logicians to study Christine Ladd-Franklin's logic, which is this woman here. So, for instance, in her doctoral thesis, which, by the way, wasn't the only work she did in logic, she published a lot of articles after her PhD study. When we focus only on her PhD study, all those topics here were approached by her work. So let's start with the first, which is philosophy with design of notation. I'll be brief in this case here because there is another workshop here, which is about the philosophy of notation. This is not the workshop, so I'll just scratch the surface of this issue. I had to make some editorial decisions here in order to make the talk easier to follow for 21st century logicians, because her notations and the way she talked, all her terminology and all her concerns were concerns from the 19th century. And we are in the 21st century, and there are some differences, logic development and so on. So for instance, her original notation choice was those symbols for her favorite relations. Perhaps they were influenced by Boole's use of V when representing particular relations in categorical syllogism. When George Boole represented particular relations, he controversially adopted a variable V with equality. So maybe it was this that influences her choice of notation. But instead of her original notation, for reasons that will become clear shortly, I will adopt this modernized notation here. So bear with me for a moment that you will understand why I decided to change her notation. But what's most important here is that the vertical symmetry of symbols is preserved here. So both notations, the old one and the modernized one, have a vertical symmetry of symbols, so nothing changes in this regard. Regarding the philosophy of notation, Ladd-Franklin adopted a clear design principle for mathematical symbols, because she was a student of Charles Sanders Peirce. They were very interested in creating iconic notations rather than employing arbitrary symbols for representing the relations and operations and so on, which they working on. Her design guidelines were the following. She argued that we should use vertically symmetric symbols for symmetric relations, and for commutative operations operators such as division, for instance. But when we see some kind of popular notation nowadays, there are many examples of notation that violates those principles stated by Left Franklin in her doctoral thesis. For instance, the minus sign. This is not a commutative operation, but we are using a symmetric symbol here. Composition of functions, which is not commutative when we are using a symmetric symbol. Usually the most common offenders are asymmetric relations and non-commutative operators which use vertical symmetric symbols. In rare cases we find in the literature commutative operators such as this one for instance, which uses a vertically asymmetric symbol. For instance, this symbol usually is used correctly in category theory, but sometimes, very rare cases, people use it incorrectly to represent both isomorphisms from A to B and from B to A. So as long as we want to use it to represent only one direction, we are safe. But in some cases, people should use another symbol when they want to represent both directions. There was Vega and her colleagues conducted a research on cognitive science, which empirically corroborated Left Franklin's wisdom here. So it was proven through experimental research that her guidelines are very sound for creating new signs, new symbols for mathematics and for logic. So this was a major contribution of her in 1883 regarding this topic. Another important issue in her research are the connections of categorical syllogistic and Boolean algebra, which I'll show you now. So let's check the semantics of her favorite relations. This relation here is conjointness, which means that E is conjoint with C. In other words, they have something common, which is not empty, it's inhabited. So it's the same thing as saying that B intersection with C is different from the empty set, or that the mean term here, this region here, is not empty. And the other relation is the exact opposite relation here, which is disjointness, which means that B is disjoint from C. You can see here by shading this Venn diagram. So it means that the intersection with C equals the empty class or empty set. And the region BC is empty. So those are the relations that, and this is one of the reasons why I chose this symbol here, because only after Left Franklin's research, the logic community standardized on the symbol for intersection of sets or classes. So in order to make a symbol which appears similar to the symbol, I made this choice. But this isn't the only reason for this. Regarding Aristotelian syllogistic, we have those four relations, those four traditional relations here. I, E, O, and A. They are with our symbols here. De Morgan showed that in order to complete all the possibilities regarding individual regions, individual mean terms here, the Venn diagrams, we had to add another four different relations here, which were, by the way, mentioned in the previous talk. Albert Memon in 1952 proposed this rotation here. He adopted the same letters from the previous relations, but he added the UNILOG over them. So, for instance, this relation here, and this relation here take all those possibilities that are enabled by the Morgan syllogistic, we can you can see here that there are 4 particular relations, those one with an x beside, and 4 universal relations, those one which have shading. So each of these relations which have an x have 4 different 4 alternative possibilities of expression, which I'll show here in this table. So for instance, when you see the relation I, it has this standard representation here by that framework, but it can be represented in 3 alternative ways too, when we consider all the 4 possibilities of particular relations. And when we see, for instance, this relation here, which is universal, the relation no BEC or BEC, we see that it also has 4 different alternative expressions. And regarding Max Franklin's favorite relations, what do we have? We have this. When we represent all of them with only the favorite relations that Franklin chose, we have those possibilities for all the relations here. So I enjoy this table because it's a kind of Rosetta Stone of the relations of categorical syllogism. Considering the extension that De Morgan made over Aristotle. Let's discuss something important that Franklin discovered, which is a property which I call the free transposition property for both of her relations. This is on page 30 of her doctoral thesis. There is an example here to make things concrete. So, for instance, this here indicates that no BC not E exists. This is equivalent to saying this to shifting to the right is simple, and saying that every BC is D or no BC is not D. And we can shift left the symbol and say that no BC is C, no B is C not D. Those are equivalent. I have some remarks here regarding this discovery by that. For instance, why have this notation? This idea here, which means x does not exist, is the same thing that x does not exist in the universe of this course. Of course, if something doesn't exist, it doesn't exist in the universe. For Left Franklin, this symbol serves a double duty as a binary and a unary relation. So sometimes she uses it as a unary or monadic relation, and sometimes she uses it as a binary relation. In such abuses of notation are not strenuous logicians, because, for instance, in the deduction theorem, we use this with the third style. She was not using something weird. Okay, I mentioned the deduction theorem here because we will approach this later here in this presentation. So, what makes this noticeable, this free transposition property, where you can carry the symbol to inside here, is that, for instance, those relations here don't comply with this property. So, for instance, you can take both sides of the subset relation, and you cannot just simply transpose them without performing some additional work. So transformations employing those relations are much harder than employing those Franklin's relations, because here you can perform transformations just by shifting left or right the relation here. And there's another point here that free transposition for both Franklin's relations generalizes the lack of existential importance in universal relations for compound subject subjects are predicatives. Because when we adopt Aristotelian syllogistic in a Boolean framework, we have to adopt it with a lack of existential import, otherwise it doesn't comply with the Boolean algebra axioms. But when we do this in Aristotelian syllogism, all subjects or predicatives are simple. They are only single terms. But in this case, for instance, this subject here is compound. In this case, the predicative is compound. This property discovered by that Franklin allows an extension of Aristotelian terminology because it allows for compound subjects or predicatives. Once you combine this with the point that those two relations are symmetric, then the idea of subject and predicative vanishes. Because if the relation is symmetric, any of those sides can be the subject. You can switch PC and not D. You can switch them. So when we combine this property, the free transposition property, with the symmetric property of those relations, we do away with the idea of subjects and predicatives, even when they are compound. So this is a major innovation of lab printings. Another point from her line is that she discovered alternatives to the entailment relation. As we will see here. It will be studied simultaneously with this topic, which is the net operator. Let's see. When we read Led Franklin's original thesis, we see these symbols here. But at that time, no logician, in the 19th century, no logician distinguished the object level from the meta level. And we know nowadays that we have to do this. So another reason for choosing different symbols for Led Franklin's original notation is that depending on the use case we have, we need to use different symbols because they mean different things in different contexts. So for instance, in term logic, we are using this, let's revisit the idea of the deduction theorem. Why is the deduction theorem important? It's important because it turns a conditional assertion such as this. You need to have a context in order to condition your assertion into an unconditional assertion. For instance, this assertion here doesn't have any context before the third style here. So it's a condition. When we apply a transformation here, analogous to this transformation from propositional logic, we obtain this. We can rewrite this as this expression here. So we have the third style here, we have it here. Then we use the NAND operator here, and we have a negation here. It's the same thing as saying the deduction theorem here. We might say, well, in this case, the entailment is still here. So where is the alternative to entailment? Well, it's indeed the case that it's always here. But when usually we are, but it's not necessarily the case that we have to make this symbol here explicit. I mean, for instance, when we have a list of axioms and a enumeration of axioms in a given axiomatic system, usually the axioms are listed without putting the symbol before. It's made implicit. So we can make a list of axioms for a given any arbitrary axiomatic system, only using this form, which is proposed by Franklin. So that's why it's important. So let's see another innovation of her, which is the idea of antilogism. When we have categorical syllogisms, they are in this format. Two premises and a conclusion. If we add to the left-hand side here, the negative of the conclusion, we can add the negative of the conclusion to the right-hand side too, because it's monotonic. But when we have this on the right-hand side, we have a falsity, because we can have a conclusion and the opposite of a conclusion together. When we apply the deduction theorem as we had shown in the previous slide, we can turn this into this. And when, notice that this symbol here represents a binary operator, because it has two sides, left-hand side and right-hand side. But remember that Franklin also made it serve double duty as a monadic operator. So we can eliminate the two here, and this remains. This is the first premise, the original premise, the other original premise, and the negation of the conclusion. When we consider this set, we form an inconsistent triad here. So let's take an example here. For instance, we have here a categorical syllogism, which is highlighted in the first figure. The usual way to state it is like this. Every S is N, no N is P, therefore no S is P. When we translate it to Franklin's notation, we get this. This corresponds to this. This corresponds to this. And this, the negation of the conclusion, corresponds to this. So we have an inconsistent triad here. Let's put this into a diagram, into a diagram. You know, we take each of those terms here and we put them into this diagram, which was a two-dimensional notation proposed by Perez in 2022, which represents K-Latent in a two-dimensional notation. How can we read this in order to retrieve the original K-Latent syllogism? If we start here from the left and we read it counterclockwise, we will have proposition 1 here, proposition 2 here, and the negation of the conclusion here. Here in this figure, we are clearly seeing where is the subject, where is the predicative, and where is the mediator or middle term here. I propose to make an abstraction here. Let's replace all those terms here, all those symbols representing the terms, by arbitrary shapes. So we will get this. Notice that we just turn them into shapes. Okay? Now let's suppose we hadn't seen the previous slide. Which here is the subject? Which here is the middle term? Which here is the predicative? No one knows because it's not obvious which is S, which is N, which is P. And this ambiguity is intentional because now we can do the following. If we start from the left counterclockwise, this way, we get K-Latent. If we start from the left but clockwise, I mean, this would be premise 1, this would be premise 2, and this would be the negation of the conclusion, would get Zums from the third figure. And if we start from the above, and we read this clockwise, I mean, in this direction, this would be the first premise. The second premise, the negation of the conclusion, we would get festinum. So with the antilogism by Ned Franklin, we get 3 syllogisms for the price of 1. That was her ingenuity here. And most importantly, if we allow 2 additional rules here, which is if we are free to switch the place of those shapes as this is symmetric, and if we are allowed to replace, for instance, this symbol by its negation, as long as we are consistent, we will replace it by its negation here, and we replace here, or when we replace this symbol by its negation and this symbol by its negation, and so on, we get 15 syllogisms for the price of 1. We can represent in a single way all the 15 syllogisms from Aristotelian syllogistic which have 2 premises without existential import. Because the other, if we consider 24 categorical syllogisms, 9 of them would require 3 premises if we don't have existential import. So it's important to notice this. Regarding the history of the truth table, Ned Franklin had a contribution to, which is this. In her 1883 doctoral thesis, she had a prototypical version of a truth table long before Wittgenstein. But it only portrays input values. I mean, they have 4 input values here with all their possibilities, all their 16 possibilities from 0 to 15. So this is an early version of a truth table, but without the output values here. We had an operator to combine those 4 forces. But there is even, when I was browsing the ancient books and so on to perform my research, I discovered an even earlier version of a truth table, which is this one, from 1646, by Meunier and Fabry in Lyon, France. So you can see here that they have veritas and falsitas, a truth table here. And even more interestingly, this logic here is a 3-valued logic, because they have true, false, and this partially true and partially false here, which is G. So there is an even much earlier version of a truth table. So for people who think that truth table was invented in the 20th century, it is a much earlier version here. Ned Franklin also had something to say about the dispute between the mereological approach, which was the most common in the 19th century, which made a partial distinction, versus the more modern set theoretic approach that clearly distinguishes elements, subsets, and sets, which at least notationally started with Giuseppe Piano. So what did she say about that? I will pretend that I will not present any spoiler here, but it's because I don't have any more time. There's a paper I wrote with the same title as this presentation for the South American Journal of Logic, so I invite you to check this. And I have merely scratched the surface of her logic in this presentation. She had many other fascinating insights. In my slides here, all the references are actually links, and they go straightly to the book page here. So I can provide you the link, and I can provide you the slide, and you can click on it, and you go straight to the source and see what is the.
We ran out of time, but it seems that we don't have enough time to just do more detail. But we have 25 minutes coffee break, so if you have questions, you can talk to our speakers here.
If you enjoyed this video, subscribe to this channel. I'll upload more presentations as time goes on. Bye.